trigonometric identity. So let's just start with what an identity is to start. An identity in mathematics is an equation that is always true for all variables, or all values rather, of all variables. Okay? So this is an identity in general. It's an equation that's always true for all values of the variables. And I'll give you an example of what I mean in a second. A trigonometric identity is an identity that involves a trigonometric ratio. So we will see things like sine, cosine, tangent, and the reciprocal trig ratios as well, cosecant, secant, and cotangent. There we go. Okay. So, for example, if you consider this statement, a plus b all squared equals a squared plus 2ab plus b squared, this is an identity. This is an equation that is always true for all values of a and b. Okay? An identity can be supported with a numerical verification, but a numerical verification is not a proof of an identity. Okay, so to prove that an identity is in fact an identity, that means that it is always true for both sides of the, for every variable of every value of every variable, that the left side equals the right side, you have to prove it algebraically. Okay, now you can support the identity with a numerical verification. So for example, if I wanted to support this identity, a plus b all squared equals a squared plus 2ab plus b squared, then I could substitute, let's say, let a equals 2 and b equals 3, right? And then I could figure out, okay, for these particular values, if I take the left side and the right side, and sub in these values, I can say, okay, well, this actually holds true when a equals b, or when a equals 2 and b equals 3, and that's in fact correct. If I sub in a equals 2 and b equals 3, I'm going to get 2 plus 3 squared on the left, which is 5 squared, which is 25. Okay? On the right, I will get 2 squared plus 2 times 3 plus 3 squared, and that is 4 plus, that's 4 times 3 is 12, plus 9, and that is also 25. So at the end of the day, the left side equals the right side. We have proved that this identity is true for the specific values a equals 2 and b equals 3. This is not a complete proof, though. It's just a numerical justification, a numerical support. Okay? To prove that this, in fact, is an identity, we need to show algebraically that the left side is equal to the right side. And when you are proving something algebraically that a left side equals a right side, essentially what you want to do is, at the end of the day, have the left side expression be exactly the same as the right side expression. So sometimes what that means is that you just work on one side and turn the one side into the other. So sometimes when you're doing an algebraic, a proof of an identity, you will just work with one side and sort of manipulate it into becoming the other side. Sometimes you work with both sides and get them both to be something else, some other type of expression, and show that those two expressions are equivalent to one another. Okay? With this particular one, my inclination personally would to be just work on the left side and expand it and show that when expanded, this a plus b all squared is in fact equivalent to this. And that is true. If we expand, a plus b all squared is a plus b times a plus b, and then we can use distribution. So this is a squared plus ab plus ab and then plus b squared. And we get a squared plus 2ab plus b squared. And then at the end of the day, the left side equals the right side. And that's what we want. So this would be an algebraic proof for this particular identity. Okay? Now, this is not a trigonometric identity, but it is, in fact, an identity. It is something that is true for all values of a and b. Okay? Now, bringing this back into trig, this is from our previous unit and also from Math 20-1. When you have an angle in standard position and a point on that circle, when we take the terminal arm and rotate it around the origin, we can call that point xy. X is the horizontal piece of that point, and y is the vertical. And then we can call that hypotenuse the radius. And when we draw an angle in this way, we can replace the trig ratios with x, y, and r. And this is something that we have seen before. We also can see that through the Pythagorean theorem, x squared plus y squared equals r squared. Okay? So this is all stuff that we've seen before. What I want to show you is I want to show you the first trigonometric proof that we're going to work with, which is a Pythagorean identity. And so I want you to sort of remember on the unit circle, r is equal to 1. Okay, so r is equal to 1. Sine theta is y over 1, which is just y. And cosine theta is equal to x over 1, which is just x. Nothing new here. We have seen this all before. But if we think about this relationship over here, x squared plus y squared equals r squared, then, and replace the x and the y with cos theta for the x and sine theta for the y, and we know the radius is 1, what we will get is that x squared is cos theta squared, y squared is sine theta squared, and r squared is 1 squared. And this identity, when simplified, is called the Pythagorean identity. And that identity, typically, for whatever reason, we write it with the sine part first, but it is sine squared theta plus cosine squared theta equals 1. And this is called the Pythagorean identity. Okay, so that's your first trigonometric identity. Okay, now, this stuff is all on your formula sheet. So, in fact, by definition, the reciprocal trig ratios are identities. They have been defined as such. Okay, so cosecant theta is 1 over sine theta, secant theta is 1 over cosine theta, etc. We've seen that before. And then what would follow is that sine theta would have to be the reciprocal of cosecant theta, and so forth, right? So these are the ones that you see on your formula sheet. These are also true. Okay, so we've seen this before, nothing new. Secondary trig ratios or reciprocal trig ratios are the reciprocals of the primary ones, and vice versa, right? So the primary trig ratios are the reciprocals of the reciprocal trig ratios. Okay, so that's nothing new. We have also seen that tangent can be written in terms of sine and cosine. Okay, therefore, cotangent can also be written in terms of sine and cosine, and it would just be the reciprocal. And on here you have your Pythagorean identities. Okay, so there are actually, in fact, 3 Pythagorean identities. I just spoke about this one. Cosine squared theta plus sine squared theta equals 1. These guys are just in a rearrangement of that first Pythagorean identity, which we just sort of came up with a moment ago. And the reason why it's just helpful to see these, although these are not on your formula sheet, is that quite often when we're using these identities, we do want to arrange the equation so that perhaps, you know, sine squared theta is the piece that's isolated. Because often what we want to do is a substitution. Okay, so it's just helpful to know that, yes, you are in fact allowed to do this. You can move things about the equal sign. That's no problem. This guy over here is exactly this same trig ratio, except that everything has been divided by cosine squared theta. So to get to here, what we do is take the original, divide both sides by cosine squared theta. Okay. Now, if I split this up into two sort of the sum of two fractions, I will get cos squared theta over cos squared theta plus sine squared theta over sine squared theta, or sorry, cos squared theta. Oh, you know what? I can't make mistakes because my pen is being weird. So I'll just have to kind of do that. Equals 1 over cos squared theta. Okay, so if I sort of simplify a little bit, this is what I get. Now, cos squared theta over cos squared theta is 1. Sine squared theta over cos squared theta, well, sine over cosine is tangent, so when I square it, this is just tan squared theta. And 1 over cosine squared theta is secant squared theta, because that would be the reciprocal of cosine. Okay, so that's this guy right here. No, sorry, this guy right here. Okay, that's the second version, but it's derived from the first. We start with that sine squared plus cosine squared equals 1, and then we divide by another trig ratio and we get this other form. Okay, so it's really not anything new. It all comes from here. I'm not going to go through this one, but if you wanted to get this one, what you would do is instead of divide both sides by cosine squared theta, you divide both sides by sine squared theta, and you would get this version of the Pythagorean identity. Okay, and then of course these ones can also be rearranged so that you isolate for something else. But these are the three that are on your formula sheet. Okay? And these essentially are just equations that are always true for every value of theta. Okay? Now, how are we going to use these? Well, at the end of the day, what we are going to be asked to do is to use trigonometric identities to prove that one thing is equal to another thing. And what that's going to involve is doing a whole bunch of substitutions. So at the end of the day, in the last line, we have the same expression on both sides. Okay? Now, oftentimes, not only does this involve using these trigonometric identities, and for today, we are only going to really be using the reciprocal ones and the Pythagorean identities. But if you look on your formula sheet, there are a whole bunch more. And specifically, there's the sum and difference identities and the double angle identities. And some of you guys have asked what I was doing on the whiteboard over here. And I was doing a proof of the sum and difference identity for cosine. So I was just kind of doing that for fun the other morning. So we'll do that tomorrow. But really, there are two main categories of identities. There's the Pythagorean ones, which are mainly just this one, and then the rest of them sort of follow. And then there's the sum and difference identities, what happens when you take the cosine of two angles added together, for example, or the sine of two angles added together, what happens there. Okay, and we're going to be looking at those tomorrow. But at the end of the day, what we're going to do is do a whole bunch of substitutions. And the hope is that we can, using these substitutions of these identities that we know are true, show that two things are equal to one another algebraically. Okay? So that includes how do we use these trig identities? Well, it includes using a lot of substitutions, but it includes a lot of things as well, a lot of other things as well. And a lot of this I would sort of put under the category of like algebraic gymnastics. There's a lot of manipulation and massaging that goes on so that we can get one thing equal to another, okay? But a couple of tips. One thing that you can always try and do is either factor or expand. Okay, so that was what I did actually with that first example that wasn't even a trigonometric identity, it was just an algebraic identity, but I expanded and I saw, okay, the left side is equal to the right side. Another thing that is helpful to do is if you're working with anything that involves a fraction, which we see a lot of with trigonometry because anything except for sine and cosine will be some sort of fraction, right? Because tangent is sine over cosine. All of the reciprocal ratios have a trig ratio in the denominator, so it's almost like a rational trig expression or whatnot. But when you are dealing with fractions, and I don't mean numerical fractions here, but I think you know sort of what I mean. Some things that you can do are simplify. So what I mean by that is add, subtract, multiply, or divide, right? And so we need to think about how do we add and subtract fractions. We need a common denominator, right? How do we simplify if we're multiplying or dividing? Well, we can cancel common factors in the numerator and denominator. If we're dividing, we multiply by the reciprocal, that sort of thing. So we have to be thinking along these terms as we go. So that's another thing that can be helpful. Another little tool that comes in really, really, really handy sometimes is the conjugate. Now you can't just multiply by the conjugate because then you change the value of the expression, but you could multiply by conjugate over conjugate, and then you're good. Now, some of you guys are like, I think I've heard that word before, but I can't really remember what it means. So the place, just to remind you where you've seen conjugate before, mainly is when rationalizing denominators in Math 20-1. But essentially, the conjugate of a plus b is a minus b. And essentially it's like sort of when you multiply them together, you get this difference of squares that happens, which gets rid of that middle term when you expand those binomial factors. And that can be really handy. And I don't really want to go into more detail right now because we are going to see lots of examples of this coming up where it'll make more sense. But that's where you've seen the conjugate before, right? So when you had something like, I don't know, 1 over 2 plus root 3, you could multiply that by 2 minus root 3 over 2 minus root 3. And then what ends up happening is that the denominator becomes rational. So that's where it's come up before. But we'll be revisiting that. Okay, so that's one really, really handy thing to do. And then the one that I always live by, and this is always usually my go-to, is when in doubt, convert everything to sine and cosine. Every trigonometric ratio can be written in terms of sine and cosine. So when in doubt, do that and work from sine and cosine. Okay, so this is usually my starting place when I don't know what else to do. Okay. So these are sort of just some tips before we get started. Okay? So now let's actually look at what some of these things look like. right? So we're going to do this both with algebraic expressions and with expressions that involve trigonometric ratios, just so that you can get a sense of the parallels. But for example, if you're working with something like this, 1 minus x squared, well, this is a difference of squares. So this could be factored, and factoring may be a helpful step in proving an identity. Okay? If you're working with this expression, this is also a difference of squares, except that one of the perfect squares is the square of sine. So 1 plus sine x, 1 minus sine x. And we saw a little bit of this in our previous unit when we were solving trig equations. Okay, this piece on factoring. Okay, and just remember, sine of x, wait a sec, I got to erase that. Sorry. Oh, that's not what I wanted to do. Go back. Pen. Okay. I don't think I can erase today because my smartboard's being weird because I restarted my computer. So let me just scribble it out. But what I wanted to tell you is that remember that sine x squared is written as sine squared x. Those mean the same thing. Okay? So here's another difference of squares. A squared minus b squared. This would be a plus b times a minus b. Okay? If we're looking at this guy, sec x plus tan x, sec x minus tan x. Okay? All right, now, rational expression type things. Often very, very handy to get a common denominator. So algebraically, if you were adding these two expressions and you wanted to write this as a single expression, this is sort of like a over 1 plus b over c, right? So we need a common denominator here. The common denominator would be c. So we would have to take this first guy and multiply this by c over c so that you have a common denominator, and now you can add the numerators. So this would become CA or AC plus B over C. Okay. This guy over here, sine x plus sine x over cos x. So this is like sine x over 1 plus sine x over cosine x. Right? So the common denominator here would be cosine x. So I'd have to take this guy, multiply it by cosine x over cosine x. And what we end up with is cosine x, sine x, plus sine x over cosine x. Okay, so you get a single expression. Now, if you can go directly from here to here, that's fine. You don't have to like show every single little step along the way, but you have to make sure that you can consistently do this correctly. And so sometimes when people try and skip steps, they make mistakes. So if you need to take some time to actually do this process of multiplying by the LCD in the numerator and denominator, please do that. Okay, so conjugate. This is what I was talking about with that conjugate. All right, so where have we seen this before? We've really seen it with rationalizing denominators, because if I multiply this expression, or it's actually a number, it's not really an expression, by the conjugate of the denominator over the conjugate, right? Can't just multiply by the conjugate. You have to multiply by conjugate over conjugate, because then you're really just multiplying by 1. And if we do that, what happens here is we get, okay, root 2 times root 5 is root 10, and then minus root 2 times root 2. So root 2 times root 2 is 2. So root 10 minus 2 over, this will be root 5 times root 5, which is 5. And then we get root 5 times root 2, so minus root 10. But then when we move on here, root 2 times root 5, we get plus root 10. And then root 2 times root 2 is root 2 times root 2 is 2. So this last piece is minus 2. Okay? Now by multiplying by the conjugate, though, what you ensure is that those middle two terms are negatives of each other. And so they equal 0. And all you're left with at the end of the day is a rational number, which in this case would be, this is 5, this is 0, and then minus 2. That would be 3. Okay, so this is where the conjugate has come up before. Yes. Sorry, did I make a mistake? What did I do? Okay, no, go ahead. I'm like bracing myself because trying to see when the first time I'm going to make a mistake is today. Okay. So far, so good? So over here, what would be the conjugate in this expression? Yeah, so we're going to multiply by 1 plus cosine x over 1 plus cosine x. Now the good news is that typically when you're using conjugates outside of rationalizing denominators, they're kind of easier to use because you can kind of see, oh, that's just like a factored form of difference of squares. So when I expand it, I'm going to get a difference of squares, right? So what you end up with here is 1 plus cosine x over, this works out to be 1 minus cosine squared x. Okay, now just a foreshadowing as to where this might be going. When I look at this and I see the denominator, I'm like, oh, that's sine squared x, because cosine squared x plus sine x equals 1. So if I take cosine squared x away from both sides, I get sine squared x, right? So we're not there yet, but those are some of the steps. That's why essentially doing something like this could be useful. When you have this, you can replace it with sine squared x, which we couldn't do before. Okay? All right, so we are just going to get very baby steps using just the fact that we know that the trig ratios on a coordinate plane in standard position can be written in terms of x, y, and r. We are going to show that this is true. Okay? So what I'm going to do is firstly, if I'm trying to show something, I want to be very aware of my left side and my right side. And I'm going to work with one side at a time. Okay? So if I'm working with the left side, which is cotangent of theta, okay, cotangent is the reciprocal of tangent. Tangent is y over x. So cotangent is going to be x over y. Okay? Cosine theta over sine theta. Well, cosine theta is x over r. Sine theta is y over r. So cosine theta over sine theta is x over r over y over r. Okay? Now, this is this fraction piece, right? I'm dividing fractions. I want to simplify that. So I'm going to take the first one and multiply by the reciprocal of the second one. And the r's end up canceling. And so we get x over y. Okay? Now I'm done because the left side and the right side are equal to one another. Okay, so far so good? All right, so let's look at this one. Now, we sort of showed this using the Pythagorean theorem, but we can also show this Pythagorean identity using x, y, and r as well. So with this particular identity, I'm not going to touch the 1. That's pretty simple. And this is another general rule of thumb. We'll talk more about this when we are, I think on Friday, when we actually start to prove these things. But typically, it's easier to start with the more complicated side than the simpler side. So start with the complicated side, simplify it, leave the simple part. It's easier to simplify something that's complex than to take something simple and turn it into something complex. Although that's not always the way things go in life. But we're going to start with this side. So cosine is x over r. So cosine squared theta plus sine squared theta. I'm just going to leave this as 1. This would be x over r squared. This would be y over r squared. Okay, and if we sort of distribute the square into each of these expressions, we're going to get x squared over r squared plus y squared over r squared, which is x squared plus y squared over r squared. Okay, now think about that little triangle, x, y, and r. What is x squared plus y squared? R squared. So the numerator, x squared plus y squared, is r squared. So I can do a substitution there. This is r squared over r squared. And r squared over r squared is 1, which is what the right side is equal to. Okay. How are we doing? So far, so good? Okay. Use the fundamental identities to express each of the following as a single trigonometric ratio or a single value. So we either want a single trig ratio or we want a single value. Okay? All right, so this first question, where might you start there? Yes?
This is just a guess, but would you just put them all into their fractions, I guess?
Okay, keep going with that. Put them all into their fractions? Yes. When I see something like this and I'm like, well, man, I only see one little sign in there. Everything else is something else. I think, okay, let's put everything in terms of sine and cosine and see where we get. Okay, so tangent. Tangent is sine x over cosine x. Tan x is sine x over cosine x. Cotangent is the reciprocal of that. So that's going to be times cosine x over sine x. And then plus, okay, that's already sine x, that's good. Times cosecant x is 1 over sine x. Okay, so the first term is actually equal to 1 because these cancel. So this is 1. Second term is also 1. It's sine x over sine x over sine x. 1 plus 1. The last time I checked, I think that's equal to 2. Okay? So this whole mess, that whole big mess, is equal to 2. This guy. All right, so where would you start here? This is already in terms of sine and cosine. So there's not much I can do there. So what is another trick that we might have up our sleeve? Is there anything to expand there? No, because it's already, there's no brackets that have been factored out. Okay, but you're on the right. Yeah, we can factor here. If you look at both terms, there is a common factor of cosine theta. So sometimes, particularly when you're not used to doing this type of thing, just rewriting this as cosine theta cubed plus sine theta squared times cosine theta can help see, oh yeah, there's a common factor of cosine theta. So I can pull that out. You don't have to do that, by the way. But in here, I'm going to have 2 factors of cosine theta left. So this will be cosine theta squared, or cosine squared theta. And here I have the sine squared theta. Okay, now how does that help me write this as a single trig ratio? Is there anything that I can replace here or substitute? Yes. Cosine squared theta plus sine squared theta equals 1. So this is cosine theta times 1, which is just cosine theta. Yes.
Why is it equal to 1?
It's the Pythagorean identity. Why is it equal to 1? Because on a unit circle, if this is 1, this is the point cos theta, sine theta. So this part is cos theta. This part is sine theta. So through Pythagorean theorem, cosine squared theta plus sine squared theta equals 1 squared, right? Which is what we have right there. Yeah. Okay, so part of these identities is understanding the why, but a bigger part is becoming familiar with them so that you can recognize that you have one right in front of you and you can do a substitution, right? Now, you have your formula sheet in front of you all the time, but even still, like, you know, when I'm looking at this, especially when I'm tired, it's like, oh man, that sheet's pretty busy. Where do I need to look, right? So the more you practice, the more familiar you will be. And at the start, we're going to sort of practice them one at a time. So for today, we're just sort of focusing on converting everything to sine and cosine and this Pythagorean identity, okay? We'll talk about the other ones tomorrow. Okay. This guy. Okay, so what would you do here? Yes. Yes, I would expand, right? We can expand this piece of it, and then let's just see where we end up, right? So if I expand this piece, I'm going to have sine x plus cosine x times sine x plus cosine x. And then on the end, minus 2 sine x cosine x. Okay? And when I now expand, I'm going to have, okay, this times this is sine squared x, and then plus sine x cosine x. And then plus another sine x cosine x. And then cosine x plus times cosine x is plus cosine squared x. I don't know why some of the letters are showing up in blue. If you've noticed that, it's not like I haven't noticed that. It's just, I don't know. And then on the end, minus 2 sine x cosine x. Okay. So how does that help?
Sine x cosine x equals 2 sine x cosine x. Then you cancel out negative.
Yeah, so this is equivalent to that, right? So it's like these make 0. So I'm just going to kind of, those add up to 0. Yeah, and then you have the Pythagorean identity, sine squared x plus cosine squared x, which is 1. It's so satisfying when you figure it out. I love this unit. Okay. This guy.
Turn them into their cosine and sine.
Yes, okay, so someone said turn into sine and cosine. Any other thoughts? So I'll tell you, if you said convert to sine and cosine, that's what I would do. But I can see where someone might think, oh, I could go another route here. And that's another thing that's really fun about trig identities, is that there's lots and lots of ways that you can show that one side is equal to another, or that you can simplify something. So the only other thing that I was thinking about here is that we could also try using the conjugate and just see where that gets us. But I think even with the conjugate, at the end of the day, we'd probably have to convert to sine and cosine anyway. Okay, so I'm going to start out by doing that. So I'm going to make this, let's see, it'll be sine x over cosine x minus 1 over 1 minus cosine x over sine x. Okay, well that looks pretty messy. So what are we going to do next? Okay, we can't cancel because nothing's factored. We got some messy looking fractions there. Any ideas? Think of this as like 1 over 1. The ones can't, so okay, the ones can't cancel, okay, because we're canceling, like if the ones could cancel, it would be like thinking, okay, if I have, I don't know, 5 minus 1 over 1 minus 4, that I can just do that. And that's not true, because this is actually 4 over negative 3. It's not 5 over negative 4. So we can't actually do that. What I was really trying to make you aware of, I guess not very successfully, is that these have different denominators. So when you have part of the expression where you're adding things that have unlike denominators, try and get a common denominator, see where that gets you. Yeah, okay? So what I'm going to do here is I'm going to take this and multiply this by cosine x over cosine x. And I'll take this one, the denominator in the bottom is sine, so I'll multiply this by sine x over sine x. Okay? And then what I end up with is in here, I now have a single denominator in the numerator. This is called a complex fraction, by the way, fraction within fraction. So in the numerator fraction, I have cos x in the denominator. I have sine x minus cos x in the numerator. And then in the bottom part, in the denominator, I have sine x. And in the numerator, I have sine x minus cosine x. Okay, so now I have fraction divided by fraction. I can now take the first one, multiply by the reciprocal of the second. And what I get is sine x minus cosine x over cosine x times reciprocal sine x over sine x minus cosine x. Okay? Now, these are sort of like in factored form. So at this point, yeah, I can cancel this factor of sine x minus cosine x. And what I'm left with is sine x over cosine x, which is tangent x. Whoops, I keep mixing up my thetas and my x's. Now I'm fairly certain, actually, that if we had multiplied by the conjugate, we should end up in the same place. Would you guys mind if we did that quickly? Or no? Should we go there? Okay. So I have to tell you, you can talk to Mr. Ma about this too. There, in every 30-1 diploma that I've ever seen in the written response, there is a trig identity question. It's usually a proof. Tan minus 1 over, okay. And when you get a question to mark, they have a very detailed scoring guide. And what they do, why we do field tests, is the field test markers take all of the questions that students, the answers that they might have, and come up with all the wrong answers. It's easy to mark something if you get the right answer. It's hard to mark when you get the wrong answer, because the question is, to what degree is it wrong? That's the hard part. So they take all the answers that people might come up with and create a scoring guide. What happens if the student does this? What happens if the student does this? How much do they get if they do this? And then we follow the guide, and there's always some student who does something crazy that nobody's seen before, and actually that happens more frequently than you would think. But I gotta tell you, for the trig identity question, there are like 5 million scoring guides, because there's so many different directions that you can go. Okay, now if we multiplied by the conjugate here, there's actually 2 conjugates that I could see working. One of them, because there's 2 sort of binomial sorts of things. I think I'm going to work with, I don't know, I didn't actually think this through. Let me look at the, okay, I'm going to work with this one. I don't know if this is going to be productive, but it'll work at the end of the day. Okay, so let's see. This is going to be, tan squared x minus 1 in the numerator. Yes? Okay. In the denominator, let's see, we're going to get tan x plus 1 plus 1, right? And then, oh, these are actually reciprocals of one another. If I take cotan x and multiply it by tan x, what am I going to get? If you take any pair of reciprocals and multiply them together, 2/3 and 3/2. 2 and 1/2. Multiply those together, what do you get? 1. Yeah. So this part, oh, this is going to be easier than I thought. That part is equal to 1, but we're subtracting because it's negative cotan x. And then at the end we have minus cotan x. Okay, so I'm going to look at my sheet. You know what? This is not easier. Do you want to keep going? We can. At this point, it's not really easier. I think at this point, I would still... No. So if I was doing this honestly, at this point, what I would do is I would abandon ship. I'm not joking. And I want you guys to see this because this is actually how you go about working with these things. You try something. If you end up getting into more of a mess than where you started, you scrap it and you go somewhere else. Did I screw something up? You guys are all waving at me, sending me SOSs. What did I do? What did I do?
No, it's nothing. It's just another way you could solve it is by turning the cotangent into like 1/10.
Yeah.
And then find the common denominator.
Yes.
Flip it and cancel it out.
Yes, you can do it that way too, actually. So that's another option. So, but my point, like, I'm glad we did this actually. This happens in calculus all the time, right? And this is where math gets interesting and fun. You see something and it's like, I don't know what the procedure is. So as long as I know what is mathematically sound to do, what I'm allowed to do, I can try it. And this is still equivalent, right? I would just argue that it's more complicated than what we started with. So that's how I make the decision. I'm like, oh, that seems more complicated. Let's try something else. Yeah. Okay, so that was a 50-50 chance, right? I saw both. The question, if you guys didn't hear, was why did I choose to use this conjugate instead of this one? And the answer to that is I was like, well, I got to do one or the other. I don't know which one to do, so I'll start with one. But yeah, I would say it's a crapshoot. Half the time I would have started with the denominator. Okay? Now I think one of the reasons why you guys may be asking that though, hopefully, just hold on a sec. Are you okay?
Yeah.
Is the desk okay? Okay. As long as you're okay. Okay, so I think one of the reasons why you may be asking that, why did I start with the top, is because the only experience that you guys have with the conjugate is using it in the bottom. Okay? But practically speaking, in the field, half the time we use it in the top, half the time we use it in the bottom. Oh, okay, cool. Why are you guys laughing? What am I doing that's so funny? Or is it like the noise outside? Do I have something on my face? If I have lettuce in my teeth, I expect you guys to say something.
Is that Zach out in the hallway?
No. That's what you guys were not. No, it was not. Okay. Okay, yeah, so again, this way I would abandon ship. No, not doing that. It's going to be more work than if I just scrap the whole thing and start from scratch. But yeah, you could start with this. Right? Get a common denominator here. That would actually work very nicely. Okay, because in the denominator, multiply this by tan x over tan x. Then you have tan x minus 1 over tan x minus 1 over tan x, right? Now this is something divided by a fraction, so we take that something, multiply it by the reciprocal of that. That's pretty sweet. That's pretty nice. That is what they would call an elegant proof, right? And I would say converting to sine and cosine is also fairly elegant, but that's not. That's a non-elegant way of going. It's going to be messy. We're going to have to take lots of twists and turns, and at the end of the day, if we continued on this path, we would get there. But again, it's more work than it's worth. And also, the more complex and the more turns you take, the more opportunities there are for you to take a wrong turn and get lost. Okay? All right. So, verifying these things numerically and graphically. So when you verify identities, you are not proving them. The only way to prove them is to do sort of what we've been doing, where we simplify, we do some algebraic gymnastics, we do substitutions with identities that we already know. But you can verify them numerically by choosing a value for x or theta or whatever you're using, and then plugging it in, showing the left side equals the right side. Okay. You can also verify these graphically by graphing each side of the equation separately and showing that the graphs overlap, right? But these are not proofs. These are just verifications. Okay? But in this course, because we're just sort of getting started with this, we may ask you to do these. And we'll see some examples of that in a moment. Okay, so for example, here are some numerical verifications, and this is where we're going to come back to that last unit that we did with the unit circle. Verify that the equation 1 plus tan squared x equals sec squared x numerically for x equals 3 pi over 4. Okay? So when we're verifying numerically, actually, we don't even want an equal sign there. We just want a chart with the left side and the right side, right? And if we're plugging in 3 pi over 4, we want to know what is 1 plus the tan of 3 pi over 4. I personally like to do it this way because I know that this is going to be a number and I'm then going to square it. I prefer to put the square on the outside than on the inside because it just helps remind me of what I need to do next. Okay? On this side, I'm looking at the value of sec 3 pi over 4 squared. Okay, so now I have to think in terms of my unit circle. Okay, here's 3 pi over 4, or special triangles, right? This is pi over 4. That's a 45-degree angle. So this point over here will be x is negative root 2 over 2, root 2 over 2, right? And the radius is 1 if it's on the unit circle. So this piece is just 1. Now, the tan of 3 pi over 4 is y over x. That's actually going to be negative 1 because you're taking a number, dividing it by itself, but with the opposite sign. So this is negative 1 squared. Okay? And negative 1 squared is just 1. So the left side at the end of the day is equal to 2. the right side, the secant of 3 pi by 4 is the reciprocal of cosine. Okay, so cosine is this guy. So secant will be the reciprocal of that, negative 2 over root 2 squared. And when we square negative 2 over root 2, well, the numerators, well, firstly, the negative sign is going to go away, because you square a negative, you get a positive. 2 times 2 is 4. Root 2 times root 2 is 2. So that's 4 over 2, which is also equal to 2. So we have verified this identity when x equals 3 pi by 4. Okay? All right, let's try this one. Verify that cosine squared theta equals sine squared theta plus 2 cosine squared theta minus 1 for theta equals 300. Okay, so again, I'm going to make my chart. And on the left side, I am going to have cosine of 300 squared. So that's really the one thing that I change. I change the notation around the trig ratios that are raised to an exponent. Okay? Because for me, it just helps me to evaluate. On the right side, I have sine of 300 squared plus 2 cosine of 300 squared minus 1. Okay, and then the other thing that I need to think about is where's that 300 degrees? So this is 300. This is 60. So this point would be 1/2 negative root 3 over 2. Okay, so the cosine of 300 is 1/2. So this piece is going to be 1/2 squared, which is 1/4. Okay, the sine of 300 is negative root 3 over 2. So this is negative root 3 over 2 squared plus, we already know what that one is, 2 times 1/2 squared, and then minus 1. Okay, now when I square this, again, it's going to be positive, because negative squared is a positive. The numerator will be 3. The denominator will be 4, 3 over 4. And then over here, I'm going to get 2 times 1/4, so 2 over 4. I know you could write that as 1/2, but I'm thinking ahead. Okay, so this works out to be 5 over 4 minus 1. And 5 over 4 minus 1, that's minus 4 over 4. That is 1/4. Okay? All right. Restrictions. So any trig ratio that has a sine or cosine in the denominator has restrictions that go along with it, because you cannot, that expression will not be defined when the denominator is equal to 0. Okay, so we need to account for that when we're working with trig ratios. They could have non-permissible values, which must be stated. Okay, so for example, if we're looking at tangent x is equal to sine x over cosine x, which means cosine x cannot equal 0. Okay, so for what angle does cosine x equal 0? Cosine x is the x value, so that's 90 degrees or pi over 2. So here, x cannot equal 90 degrees plus or minus 180 degree n, where n is an element of the whole numbers, because it happens at 90, 270, then you keep going around, right? It happens on the y-axis, essentially. In radians, x cannot equal pi over 2 plus or minus pi n, where n is an element of the whole numbers. Okay, now secant x is 1 over cosine. So cosine x, again, cannot equal 0. So actually, these have the same restrictions because there's the same trig ratio in the denominator, right? So I'm just going to do the ditto marks. Okay, now cosecant x is the reciprocal of sine. So in this case, sine theta cannot equal 0. Okay, so where does sine theta equal 0? 0 degrees, and then it happens every 180 degrees, right? So this would be x cannot equal 0 degrees plus or minus 180 degree n, or x cannot equal 0 plus or minus pi n. Okay, and in fact, I'm curious, when you guys are thinking, when I ask you, when is cosine equal to 0? Are you guys envisioning the unit circle? Interesting. That's so interesting. I don't do it that way. So what I do is I think about this. I think about it graphically. And I don't know, for me it's easier. But whatever floats your boat, right? Happens 0 and then every pi. So anyway, whatever. Multiple ways. It doesn't matter. It's 6 of one, half a dozen of the other. Okay. All right. Cotangent is also cosine over sine. Oh, you know what? I realize I apologize. I'm not going to erase this because my eraser is not working today, but I keep going back and forth between theta and x, and I really should be consistent. So I'm just going to make this there. Let's do that. That's easier. So again, sine theta cannot equal 0. Oh, and look, I did it. Oh, man. I'm not even going to bother. I'm doing a terrible job here. I'm using x's and thetas interchangeably. Don't do what I do. Okay, so this is the same because it has the same restriction. Okay? So that's just something to think about. Okay? Next, another verification. The verifications are usually, you plug it in, you evaluate each side. You do have to simplify, and you have to simplify exact values, so that can become a little tricky, but usually pretty straightforward. So here we are numerically verifying that this is true when x equals pi over 4. So we have our left side and our right side. So we've got tan pi over 4 times sine pi over 4 plus cosine pi over 4. And here we have secant pi over 4, right? So, I mean, to remember what these trig ratios are, you may want to visualize where that angle is. It's in the first quadrant. It's equivalent to 45 degrees. So this point is root 2 over 2, root 2 over 2. Okay, so the tan is y over x. That's going to equal 1 in this case because y and x are equal. So this is 1. Sine pi over 4 is root 2 over 2. Cosine pi over 4 is also root 2 over 2. So what we end up with is root 2 over 2 plus root 2 over 2. That means we have 2 of them. And the 2's cancel, so we end up with just root 2. Okay, now on this side, secant is the reciprocal of cosine. So cosine's my x value. So the secant will be the reciprocal of this. It'll be 2 over root 2. Okay? Now, these at this point don't look equal. So here's what you can't do. You can't put them into your calculator as a decimal and say, oh, they're both the same decimal. That does not count as a numerical verification. When you're verifying numerically, you have to stay in exact values all the time. Okay? But we can rationalize the denominator, and hopefully that'll work. If we multiply this by root 2 over root 2, then this becomes 2 root 2 over 2, and then you end up with the same thing. Okay? All right. So how can you verify? So we're working with the same question. How could you verify this graphically on your calculator? So we're not actually going to go through this, but the way that you would verify it is graph y1 equals the left side, which is here. And y2. Now, you don't have the secant ratio on your calculator, so you would have to enter it as 1 over cosine x. And then you would just show overlap. Okay? All right, so now we're going to get to the fun stuff, and we're actually going to prove that this is, in fact, an identity, meaning that it is true for all values of x. All that we've done so far is show that it's true when x equals pi over 4. And if we went through the motions of graphing it on our calculator, we would see that just within the window that we can see, which is a very limited window, it is true for that window. But you can't see, if the domain is infinite, you can't see every possible value when you're doing things graphically. Okay? All right, so we're going to prove it. All right, so what would be your instinct if you were proving this identity? Where would you start? Yes. Go to sine and cosine. Revert to, I can't talk today. Revert to sine and cosine. Okay, so tan is sine x over cosine x plus cosine x. And secant x is 1 over cosine x. Okay? So now what? Firstly, which side would you work on next? Yeah.
What? I don't know.
Oh, I missed the sine x, didn't I? That makes a big deal. That's a big deal. I shouldn't have missed that sine x. Otherwise, this would not be true. We'd run into big trouble. Thank you. Okay. Where would you go now? So first, okay, let's start with this. Would you continue to work on the left side, or would you continue to work on the right side? Left, because it's more complicated. Okay. So I see some sort of sum there. So I would work on that sum. What's the denominator here? Yeah. So let's get a common denominator and see where that takes us. Okay. What is the common denominator between these two? Yeah, so I'm going to take this term and multiply it by cosine x over cosine x. And then what I end up with is a single denominator of cosine x. This is sine x times sine x, which is sine squared x, or sine x squared. And this one is cosine x times cosine x, cosine squared x. Okay? So now what? We can't factor. Yeah? Yeah. The numerator is equal to 1. And now we have, okay, left side equals right side. Now, when I was in university and you had you finished a proof and it was elegant, I have to look up what this means But you would do this at the end. I don't know what that means. It comes to Latin. It's some sort of abbreviation that shows that something was elegant. I want to know. We're done because we actually already did this one. Remember? Show that this is equivalent to this. What did we do? What did we do to get from here to here? Think about just comparing this and this. What would you have to do to cosine squared theta to get it to be 1? Divide it by itself. Excellent. Yes. So I'm going to divide this by cosine squared theta. Now, if I do that, I got to do it for everything. There we go. This is 1. Sine over cosine all squared is tan squared theta. Reciprocal of cosine is secant. There we go. And the other version of the Pythagorean theorem works the same way, but instead of dividing everything by cosine squared theta, you divide everything by sine squared theta. Okay. So that's it for today. Tomorrow, we're going to start working through all of these.